Okay, so in the last lecture, I want to talk about something slightly different, inverse problems in energy minimization. But before I start, let me just thank all of you for coming. And it's been a lot of fun to do all these lectures. And also thanks to the guest lecturers, of course, for lecturing. So, okay. So we want to talk about inverse problems. Energy minimization. And thanks to the organizers, Naru and Mahesh. Where's Mahesh? Mahesh is there for organizing. Okay, so I will focus mostly on spherical codes, but here's the sort of the inverse problem. I'll say a few words about the Euclidean case, but the problem is the following. So most of the time we've been talking about you have some potential energy function, and you're trying to minimize potential energy among spherical codes or or configurations in Euclidean space of some density. Now here we're going to try to do the other thing. You have a target code that you want to make. Can you design your potential function to make it as the global minimum? So given a spherical code C, can we find potential function f such that C is unique global minimum for F potential energy. So we want to make this code somehow. So for some codes, some nice codes that we've seen, like the regular tetrahedron, the octahedron, the icosahedron, you can just give it 1 over inverse power law potential, and it will global minimum will be that code, as we've seen, because they're universally optimal. So some codes such as regular tetrahedron, octahedron, icosahedron, or 600 cell, any completely monotonic function of squared distance f will do, right? So that will be optimized at this code, since they are universally optimal. So that's sort of the easy case in some sense. Most of the time that's not going to be true. You're going to have some some code that's not obviously if you put an inverse power law, you're not going to get something that converges to that code. So others, such as, let's say you take the cube, the regular dodecahedron, even the duals of these things, or the dual of the 120 cell, the 600 cell is the 120 cell, etc. You have to work harder. So if you put 8 points down and you give it 1 over distance to some power, it's going to become a skew cube rather than a cube. So what do we need to do? For very general C, it's not even clear there exists such a potential function. Okay, that will be minimized by that code C. So which codes could possibly be solutions of energy minimization, and how could you make the appropriate potential functions? So before I say some more words about this, let me just say that for Euclidean space, there are some experimental results these physicists, Rexman, Torquato, and Stillinger, I guess they're physicists, chemists, and material scientists. Stillinger, they describe potential functions for which some specific periodic configurations or lattices seem to be the minimum, right? So for example, the simple cubic lattice, just z to the n, or the honeycomb periodic structure. So honeycomb is what you get if you take the A2 lattice and you sort of remove some points out, and it looks like a bunch of hexagons, or just like you see in a honeycomb, right? Or diamond in 3D. These things are conjecturally optimal. So I mean, if you simulate, you get these things, but we don't have a proof, so computer. So they did a lot of computer experiments, seem to make these lattices. So let me just give you some references. They're quite nice papers. So targeted. So the key word is self-assembly. Self-assembly. Something involving honeycomb lattice. Honeycomb. So I guess I should say physicists use the term lattice to mean periodic configuration. So lattice, and they use the term Bravais lattice to mean lattice. Okay, so that's just physics terminology. So when they say honeycomb lattice, it means the periodic configuration, which is the honeycomb. And so this is in phys rev let. There's something called self-assembly of simple cubic lattice. So z to the n, right? I mean, you don't expect z to the n is going to minimize anything, normal, like 1 over distance decay. Certainly in 2 dimensions or in up to 8 dimensions, it does not seem to do anything of the sort. This is in phys rev E. There's synthetic diamond, and wordsight, also in phys rev E. And they have another one called designed interaction potentials. For self-assembly, also in phys rev E. So the point is, if the potentials are simple enough that you could somehow make them in lab, if potentials are simple enough, and we could simulate them in a lab, so to speak, then you could make these materials. So could make these materials synthetically, right? So sort of you provided the potential function, and things self-assemble and make whatever you want to make. So it's going to have some applications potentially in material science or nanotechnology or what have you. Okay, but there are no proofs. Okay, so these things don't. Okay, for Euclidean space. So the compact case is easier to handle, so that's what we'll be focusing on. Compact case sphere, and we'll try to focus on things we can prove rigorously. So it's easier to handle, and hopefully the techniques should be useful. in the Euclidean setting too. So we're going to consider designing structures in the sphere. So let's consider designing structures on sphere. Okay, so you want some spherical code, you want to make it. So d be, so C is the spherical code you want to make, and let d be the distance distribution of C. Distance distribution of C. So namely, for every distance between 0 and 2, you figure out how many times it occurs. So d is the function such that d of r is the number of pairs of points of C at distance r. Okay, so that's our distance distribution. So in order for d to be the global minimum, for C to be the global minimum of EF for some f. So notice that we are only looking at potential functions of distance, so pairs of points. So everything just depends on the distance distribution. And so this distance distribution should have the following properties. So we need the following properties to hold. So one, C is the only spherical code with its distance distribution. Distance distribution. D, since D and F determine the potential energy EF of C. Right? If it wasn't the only spherical code with its distance distribution, if there were another one, it couldn't possibly be the unique minimizer. Any other code with the same distance distribution is going to have the same energy. So uniqueness is out the window if that's not satisfied. Sorry? Up to isometry, yeah. Up to isometries, right. Oh. Okay, and two, I guess in whatever permutations, etc. So D must be, here's the other thing that it must satisfy. It must be extremal. So this distance distribution must be extremal. In other words, it cannot be written as a non-negative weighted average of other distributions with that number of points, C point distance distributions. If it was a convex combination of some other ones, then one of them, for whatever potential energy you have, at least one of them would have smaller or at most the same energy as C, right? Since otherwise one of them is at least as good as D. And distance distributions of actual codes, that's what I mean, for any choice of potential energy. Okay, so it must satisfy these two conditions if one has to have any hope of minimizing being the unique minimizer. So let me give a sort of example which illustrates the second point. So consider the following 3 configurations in S3. So A, 4 points. So this is an R4, in other words, all orthogonal to each other. So then D of A is just all of them are at square root of 2. Okay, so it's just 6 Dirac delta of square root of 2. B is just a square on a 2-dimensional S1 inside there. So then D of B is just, so you have 4 things. So the radius of the square, the radius is 1, so all these are square root of 2, except you have 2 diagonals which are 2. And then C, 3 points at vertices of a square, and 1 point orthogonal to all of them. And then you can compute that D of this distribution is 5 delta square root of 2 plus delta 2, right? So you have only one diagonal. And this is obviously the average of those two, so this cannot ever be, and C cannot be the unique global minimum for any potential function. Okay, so that's sort of an example showing that condition 2 actually does bite. Okay, so then the first theorem is that these necessary conditions are also sufficient. So if, and I'm not making any constraints on what the potential function might look like, except maybe it has to be continuous or something. If I allow reasonably arbitrary potential functions, that this is sufficient. So theorem. So this is this paper. Let me just write down the reference. It's called Algorithmic Design of Self-Assembling Structures. This is PNAS 2009. Okay, so that it's in that paper. So these two necessary conditions are also sufficient. Okay, so let me sketch the proof. So the basic idea is we're going to choose a potential function which has potential wells at all these, at the inner products which are in the distance distribution. Okay, so we will choose potential function with deep wells sort of in the support of D. So I mean, one way is clearly necessary. So yeah, so we were just trying to show this is enough. So you find a function. So first thing is we find function L defined on sub D, on the support of D, such that D is the unique minimum of T goes to sum of R, L of R, T of R among C point distributions with support T contained in support of D. So this is basically saying D has some discrete support, some finite set of points in which you're supported. Now you can have many, many codes perhaps which are supported at exactly those distances. The distances don't necessarily determine the code. There may be others, but whatever they are, they define some other distance distribution T, and it's saying, you have some finite number of distance distributions because you can only have an integer number of points at each distance, and you make it so that this guy, which is by assumption is extremal, it's not in the convex hull of all the others, is therefore extremal. So you find so this is a linear programming problem, in other words. I mean, this is a linear program. You can find a supporting hyperplane which touches at your distance distribution D. Because you find a linear function which does that, L of R, makes this one optimal among everything which is on the support inside the support of D. So you can do that. So this is possible. Because D is extremal. Okay, now for epsilon, small epsilon, you choose a smooth function f epsilon. So these are sort of the depths of the potential well. L of R you think of as the depth of the potential well, but you choose a smooth function such that if you're more than epsilon away from anything in the support of D, the potential energy is too large. So already you're disqualified, okay? Such that f epsilon of S is bigger than this entire sum over R L of R d of R. This is the potential energy of D with respect to the function that we've chosen, L, whenever S is not within epsilon of a point in support of D. Okay, so whenever you're too far away from the support of D, already you're disqualified, and also such that f epsilon has strict local minima at support of D, at the points of support of D. Okay, so then it's basically clear what's going to happen. You're forced to lie within epsilon, and in that region, there are only finitely many possibilities, and there's a sequential compactness argument which tells you that if epsilon is small enough, the only thing you could do is to optimize is to be at the distance distribution D. So epsilon small enough, f epsilon will have strict global minimum at D and therefore at C. Because C is the only code with that distance distribution. Okay, so that's roughly how that argument goes. Okay, so we've used potential wells which are not exactly the most present functions, but I mean this is a proof of concept, so to speak, saying this is necessary and sufficient. Really what we want to do is get nicer functions. Okay, so used potential wells to get a proof of existence. We'd like to use nicer functions. Example, we would like functions which are potential functions which are decreasing, and convex. Just these two conditions, let's say we wanted to impose. As long as we have a reasonably nice code that we want to make, we should be able to do something like this. Function of distance. at least if C is nice enough. Okay, so for nice examples like the cube or the dodecahedron, we ought to be able to do something like that. So obviously, we cannot always use completely monotonic functions, so this may be as far as we can go. Cannot always use completely monotonic functions of distance or square distance. Okay. There's an easy theorem which says that if you have a completely monotonic function of distance, then it's completely monotonic also as a function of square distance. Basically, because if you look at the function square root of x, it has appropriate derivatives. So you can use the chain rule. All right. So let me just note that being decreasing and convex are linear conditions on F. On the function, right? You're just imposing the derivative is linear, so you're just imposing a linear condition at some point. So for example, if you're looking in a fixed space of linear space of functions, it's finite dimensional or something, these are all linear. So linear space functions. Okay, so what we are going to do is next is you're actually going to use the Euden's linear programming bounds for potential energy to give examples where we can provably show that something is globally optimal. So we're going to use Euden's LP bound for energy to find nice functions in many examples. So for example, I mean, the functions that we'll produce will be decreasing and convex. As a function of distance. All right, so let me write down an example theorem. Here's how you could make the cube. So let f be the following function. F of r is 1 over r cubed minus 1.13 over r to the 6th plus 0.523 r to the 9th. Okay. So this function is actually, so this function, the function f is decreasing and strictly convex, and the cube is the unique global minimum for F potential energy. Among 8-point codes in S2. Okay, that's a theorem. So how do we prove something like this? So proof sketch. So it'll turn out that it's actually, you can prove it by linear programming bounds. So let H be the unique polynomial of the form H of t is alpha 0 plus alpha 1 p1 of t P's are the Gegenbauers in this case, plus P2 of alpha 2 P2 of t plus alpha 3 P3 of t plus alpha 5 P5 of t. I skipped 4. Okay, so Pi Gegenbauer. Those are Gegenbauer polynomials. So which agrees with, so H is a unique such polynomial which agrees with your given function f of square root 2 minus 2t to order 2 at the inner products different from minus 1 and to order 1 at minus 1 and order 1 minus 1. So in particular it stays below the potential function, and it's positive. You can check these things turn out to be positive definite. So one checks that H satisfies the conditions of Euden's theorem, and that the cube is compatible with H. What I mean is, by compatible I mean two things. One is whenever you are at an inner product of the cube, one of these things, that H agrees with F, that we did by construction. And the other thing I mean is whenever a coefficient in here is non-vanishing, then the corresponding sum over Gegenbauer is vanishing. Okay, so that's correct. So H of t is determined. So F is given, and then H of t, there's exactly one way to interpolate at those points. Right? I guess there are 1, 2, 3, 4. So 5 conditions, and so 2 conditions for double interpolation at these points, and 1 more for at minus 1. So it fixes what the thing is. So i.e., where was I? So whenever alpha I is positive, I mean whenever alpha is not 0. So all these alpha i's are non-negative. You can check that by direct calculation. And whenever it's not 0, namely, 1, 2, 3, and 5 for I not 0, so I bigger than 0, then Pi, this sum Pi of xy for xy in the cube, that sum is 0. Okay, so it's like the design property. The problem is it's not a, so the cube is not a 4 design, so you can't use P4, but the fifth one does vanish, and so you can use P5. That's the key. So you can still interpolate, and you can still basically, so that's how you get that f of r. Right, so this is the case. True for the cube by explicit computation. So that shows optimality. That shows that this thing is optimizes. It gives you a sharp bound for that potential energy. With that potential energy is not completely monotonic, but at least it's decreasing and convex. One can check. And if you want to see uniqueness, you want to show that it's the unique minimizer. That also you can use a little bit of combinatorics to check uniqueness. Suppose you have some code C, which is not necessarily the cube, not necessarily cube. Suppose that's compatible with H. So then that means that, first of all its inner products must be the same as in the cube. So since H agrees, so it gives a sharp bound, and the only way to do that is, first of all, you have to vanish whenever, so H agrees with f of square root 2 minus 2t only at those points, only at t equals -1 or plus -1/3. The first thing that shows you that these are the only possible inner products between distinct points of C. So that's the first thing that you deduce. And then also for C, if you fix a point y in C and I is between 1 and 3, then you can look at this polynomial pi of xy as a function of x, okay, on the sphere, right? So you're fixing a point y in C and you're looking at this as a function of the sphere. Its average over the sphere is 0, and therefore it follows that it has to be, by that property, it has to be it has to satisfy that the sum of this polynomial over C is actually 0 by compatibility. Okay, I mean that follows from the sharpness. All right, so this gives you something quite interesting. So it's a spherical, at least it's a spherical 3 design. And you can use this to compute the number of points that are at distance that are at inner product -1 from y, and it turns out that's always 1 irrespective of what y is, and the number of points that are at either of these distances, and that's always 3, where n sub t is number of points in C which have inner product T with this fixed y C. So just let me indicate how this follows. This is something that's actually used in all the uniqueness proofs when you have a design. And what you do is you've taken this particular polynomial pi of xy, and you then just write down that sum. So for each y in C and I between 1 and 3, you get pi, when you make that sum, you get that pi of -1 times n sub -1 that many times, plus pi of -1/3 n sub -1/3 plus pi of 1/3 n sub 1/3 plus pi of 1. N sub 1 is 1. So this whole sum has to be 0. Okay, so this is true for I between 1 and 3. You have 3 variables and 3 equations. Okay, so you can solve this uniquely, and so 3 linear equations. So there's a unique solution, and you can solve. I mean, you know what these PIs are, so you can just solve them out. Solution that n minus 1 is 1, n plus minus 1/3 is 3. Okay, so this followed by designacity. I mean, by exactly this condition that this sum has to vanish. All right, so once you know these local valencies, so you know that every point has an antipode, and you know that every point has 3 points exactly at this angle cosine inverse 1/3. So for each point in C, you can consider its 3 nearest neighbors, and they must have inner product minus 1/3 with each other. I mean, first of all, you can't have 2 things being antipodal, because if 2 of them were antipodal and had inner product minus 1, then you would see inner product minus 1/3, then rather than 1/3 with this point of C. So, and then you can't have inner product too close, 1/3 between two of them, because that would imply that some other pair of points had further distance, and that's not possible either. So there's some local arguments that you can make. So local configuration is same as a cube, and you can do a little bit of geometric reasoning and see that this determines the entire structure. So that shows that C must be the cube. So a little bit of argument to do there, but it's not very hard. Okay, so that shows that it's the unique global minimum. Okay, so the general strategy is, if you want to make some nice configuration and you want to make it with a nice potential function, what you can do is you can use exactly the Gegenbauer polynomials that sum to 0 over that code. So in general, strategy is can use only the Gegenbauers that sum to 0 over C cross C. Okay, and we can use as many as you want. You can use as many as needed to make sure C is determined from the data the data that falls out of valencies, which are these n's, and there's also things like intersection numbers, which are, if you have 2 points at a particular angle in a product, then how many points are there at particular angles from them. So intersection numbers, etc. That we can obtain from the sharpness of the LP bound. And then, so you can use all these Gegenbauers, and then you try to add a function that's decreasing and convex to add a function that is decreasing and convex, usually by adding on a term of the form product of t minus ti, where I runs over t minus ti squared, where I runs over inner products of C, divided by R, where, so say where t is 1 minus r squared over 2, the inner product, and then the ti, so in P of C is inner products of C distinct from 1. Okay, so that's sort of the general strategy. You might still not get something that you know as nice as you want. One may not always be able to get a decreasing convex function. So I want to give a couple more examples. I think I'll give you an example for the regular dodecahedron and a fairly complicated example for the 120 cell. And then I'll talk a little bit about an algorithm, and then that'll be it. I'll end with some open questions. here's the theorem. This is the dodecahedron. Okay, so let f be the following function. F of r is 1 plus, so it's going to be t in terms of t, where, let me just say where t is 1 minus r squared over 2. So 1 plus t, so everything is in terms of r. Eventually in terms of r, 1 plus t to the fifth plus, I'm going to write exactly something of this form. So t plus 1 squared, t minus a third squared, all the stuff that shows up in the regular dodecahedron, t plus a third squared, t squared minus 5/9 squared divided by 6, 1 minus t squared. So it's not exactly r in the denominator, but a power of r, but something similar. Okay, so it's r to the fourth. So the theorem is that regular dodecahedron is the unique global minimum for EF among all 20-point codes on S2, and the function is decreasing and convex. F is decreasing and strictly convex. So I won't go through the proof of this, but let me just note that the auxiliary function you would use is just this thing. So h of t is exactly 1 plus t to the fifth, and that's okay because it's the dodecahedron is a 5 design, so it turns out to be enough to show it. Okay, so one more example. The 120 cell, which is the dual of the 600 cell. 600 cell is universally optimal. The 120 cell is not. But you can make the 120 cell with a reasonably nice potential function. So at some point I coded all these up, and I had a simulation which would actually converge. You do gradient descent, and it shows you the points converging. So I have that on my computer, but it's fun to sort of actually see them nicely converge. 120 cell. So let C be the 120 cell, and Q of t be the product of t minus ti, where I is in, so ti not equal to 1 in the sort of the inner product of C. Okay, all the inner products. All right, so in this case it's a long list, so let me write it out. So Q of t turns out to be t plus 1, 4t plus 1, 4t minus 1, 4t plus 3, 4t minus 3, 2t plus 1, 2t minus 1, 16t squared minus 5, 4t squared plus 2t plus 1, 4t squared. So you can see it's a very long list of inner products, and there's no way this thing is going to be a strong enough design, right? I mean, in the sharp configuration sense, it's not going to have 2m minus 1 designicity, but it has enough things that Gegenbauers that vanish that we're still able to do something with it. Keep going. So 4t squared, 16t squared plus 4t plus 1, sorry, minus 1, 16t squared minus 4t minus 1. Oh, there's more. 16t squared plus 4t minus 11, 16t squared minus 4t minus 11, 16t squared plus 12t plus 1, and 16t squared minus 12t plus 1, 16t squared plus 20t plus 5, 16t squared minus 20t plus 5, and normalize by 2 to the 50 because we want it to be monic, just for case. So there's a powers of 2 in the t's. So okay, so that's how many inner products there are, all the roots of this thing. Then right, then what are the gegenbauers which vanish? So let m1 dot 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 m29, there's 29 of them that we need to use, be the integers 2, 4, 6, 8, 10, 14. So 12 is not 1, 16, 18, 20, skip 22, skip 20, so 22, 26, 28, 34, 38, 46, and 1, 3, 5, 7, 9, 11, 13, 15, 17, 19, 21, 23, 25, 27, 29. The odd ones are always okay because it's antipodal code, so you can use all the odd ones you want, but not all the even ones. And C1 dot 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 C17 be the following rational numbers: be 1, 2/3, 4/9, 1/4, 1/9, 1/20, 1/20, 1/5, sorry, 1/15, 1/15, 9/200, 3/190, 0, 7/900, 1/40, 1/35, 3/190, 1/285. Okay, and this is just to say that you can make everything nice and rational, okay, which you did. Okay, so the theorem, the potential function defined by f of r. Again, t is 1 minus r squared over 2. Sum from I goes from 1 to 17 of ci pi of t plus. So this is going to be your auxiliary function, sum of I going from 1 to 29 p sub mi of t 10 to the 6th plus 10 to the 5th q of t squared over 1 minus t, where t is r squared over 2. That is decreasing and strictly convex. Convex. And the regular 120 cell is the unique regular unique global optimum for f among all 600 points codes on S3. So this one is extremely complicated, but maybe there are simpler ones. We just went with our technique, and that was the simplest that we could come up with. All right, so you can make some of these things, and it would be fun to try to do this for other interesting configurations that we know of. These are the ones. These are some of the ones that we do in the paper. I think we also do the 4-dimensional hypercube. Okay, the last thing I want to say is describe an algorithm which does the following, which tries, it's a heuristic algorithm which tries to solve the inverse problem for a given target configuration. Okay, so we'll call this simulation guided optimization. So we describe a heuristic algorithm which tries to solve the inverse problem for a given target configuration C. And C has to satisfy those necessary conditions that I mentioned. Satisfying necessary conditions. So it's heuristic in the sense that it's going to end with something, a function that, most likely has C as the global minimum, but we don't know for sure. Okay, I mean, we have reasonable confidence, and you'll see why when I describe the algorithm. But it's not it doesn't provide rigorous proofs. Okay, so the idea is the following. So suppose we're going to start with some space of functions. Suppose we're only allowed to choose a linear combination of a specified finite set of functions f1 dot 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 fn. So whatever a potential function is, it should be a linear combination of these for our potential function. Okay, so it could be something like, you take different powers of R, or you take some polynomials in T, and so on, and some finite set of functions, and you want to make a linear combination of these which optimizes C. Okay, and this is just to make everything finite dimensional. And and we want to impose some additional constraints on f, which is going to be sum of lambda I fi, some linear combination, which we're going to assume all the constraints are linear, which we assume are finitely many linear constraints. Linear conditions. Let's say your set of conditions is P, and these are going to be some linear conditions on the lambda i's. Okay, so for example, if you wanted to, so here's how you could approximate being decreasing and convex. If you wanted to say this function you want it to be decreasing and convex, well, that's an infinite set of conditions. You take the derivative and you want that to be negative. So it's saying lambda I fi prime, the sum lambda I fi prime at every point has to be negative, but you can approximate it by saying there's a fine enough mesh of points and you're just forcing it to be negative at those points. And so you can make an approximation of that sort. Okay, so the FIs are, I mean, you choose some reasonable space of functions like 1 over r squared. You could choose, fi being, fi being 1 over r to the I, and you go up to some power, or you could choose, some polynomials in 1 minus r squared over 2, the t. So things like that. I mean, some reasonable space of functions, and you're just trying to take linear combinations and see what's the simplest you can come up with. So, right. Let me just write down what I just said. So for conditions such as decreasing convex, can approximate the interval from 0 to 2 by fine enough set of points to get finitely many linear conditions. Okay, and finally, to keep the potential function bounded, we'll add the constraints that all the lambda I are bounded by 1 an absolute value. So all the lambda are between -1 and 1. So these are linear constraints. We'll add them to P. So at any stage of the algorithm, so I'll describe the algorithm next. So at any stage of algorithm, we'll have a finite list of competitors to C. Okay, C is the code we want to make. We'll have a finite list of competitors. C1 dot CL. That list might increase or decrease. It's only going to increase actually. So this list might increase, but we'll have some list of competitors. C1 to CL. Okay, so here's the algorithm. So you start with any choice of coefficients, lambda I. So for example, you could say lambda 1 is 1 and others are 0. And an empty list of competitors. Okay, you start with something and then you solve. The second step you do is you solve the linear program with variables lambda I and constraints given by all these constraints, linear constraints that we put, P, as well as one more constraint. So well, as well as the following constraints, as well as the inequalities that say that EF of C, remember this is some F is linear combination of the Fi, so this is some linear function of the lambda i's. Okay, so EF of C is less than or equal to EF of Ci minus delta, where delta is another variable with objective function delta, which we want to maximize. So what this step is doing is it's finding this linear program, it's setting up this linear program, it's saying this code is better than, has smaller energy than all the other codes by at least delta, where I'm going to try and maximize delta. So I'm going to make as much better as it can than all the competitors. Okay, so this ranges over all the competitors, Ci. Okay, right. So then you solve this linear program. If delta is negative, if you can't be better than all the competitors, then you already failed. Okay, I mean, and that's provably, right? I mean, that's telling you that this linear combination cannot do better than the others, and so automatically cannot be the unique global minimum, or the problem is infeasible, which also happens sometimes. You stop and return, fail. There is no solution. Solution to this inverse problem. So in this, I mean, at least among the linear combinations of these functions that you've chosen, I mean, you might want to start with a different set of functions and try again. Okay? If it's positive, if delta is positive, you have solved something. So then what is it going to give you? It's going to, so remember the variables were lambda I and delta, and it's given you a set of variables lambda I. You compute the sum of lambda I Fi, gives you a function f. So you update f. So use the solution to update f, and then you run the simulation. So choose C random points on Sn minus 1 and minimize energy, you just run a simulation by, let's say, gradient descent, by gradient descent. For example, to produce another competitor. So either it converges to C or it converges to something else, which may be a local optimum or whatever, or a global optimum for that F. Another competitor to C, if we get different answer from C, right? If you don't converge to C, when you run that simulation, you might converge to something else that gives you another competitor. Put that in the list of add that to the list of competitors, and you repeat this experiment many times. Right? This step you run with the same F many times. You produce a whole bunch of competitors and add them to the list. And then finally, so if we've produced sufficiently many competitors, and the result of the previous step is always C. So if this step is always converging to C, then you can be reasonably confident that you have produced a function that is globally minimized by C. Otherwise, so then you can stop. So then you stop and return F as a putative solution to the inverse problem. Else, if it's producing other competitors, then you go back to step 2. Step 2 with the augmented list of competitors. And then you run the linear program again, and so on and so forth. Okay, so you keep going. So that's the algorithm. I mean, there's no sort of running time analysis. Like, you don't know how long this is going to take, but you can try to run this for any target configuration. Sorry? No, it's not clear. Yeah, that's why it's a heuristic algorithm. It's not clear that it'll end, and it's not clear that when it ends that you have something that's provably optimized. But it's, the longer it runs, you get some more. I mean, you get more confidence, and also if it's a finite dimensional space, you can sort of imagine that there's only finitely many other local maxima that you can get, and so hopefully either you will fail at some point or get something that's reasonable. Okay. All right, so the last thing I'll say, and then we'll stop, is let me mention some open questions. So you can try to do this inverse problem, the rigorous one, so for which n can we make the n-dimensional hypercube with, say, a decreasing convex function So this is something that should be reasonable to solve, but we certainly haven't worked it out. So it would be a nice research project. So another question is, so to improve this heuristic algorithm for simulation guided optimization, to sort of, to A, guarantee that it terminates, and B, make it faster. So that would be interesting to do. Third question is how would you do this for the things that Torquato, Stillinger, and Rexman were talking about? So how to do this in Euclidean space for configs in space. So the analog for the kinds of things we've used, the Gegenbar polynomials, is are functions with positive Fourier transform, Bochner's theorem, and the analog of interpolating is interpolating at. Now, the main problem is you have to interpolate in infinitely many points, namely the points, the vector lengths of the target configuration that you're doing. But it looks like we have some advances now as to how to interpolate at infinitely many points. So there's a lot of interesting work potentially that lies there, how to interpolate reasonably, how to do Fourier interpolation for other sets of distances. So that's a fairly big open problem. But what if you could do that, then you could possibly rigorously prove things like, the cubic lattice is the global minimum for this potential function. So there are some examples where people have, I think there's one example where people did this in 2 dimensions, but for, with some Leonard-Jones type potential for the hexagonal lattice, but certainly not for any of these lattices that they, or periodic configurations they talked about. So that would be worth doing. And then finally, not only do you care about the global minimum, really what we care about are the local minimum. When you run the simulation, it's really going to probably converge to some local optima, which has a large basin of attraction. So really, we should be talking about local optima with large basins of attraction. So how do we achieve that? How do you make a global or local optima with a large basin of attraction? As far as I know, people have no idea how to do any of this. So these are quite, some of them are quite hard open problems. All right, we'll stop there. Thanks. Thanks very much. Thanks to ICTS for hosting us. Yeah.